Good afternoon. It is a pleasure to be here at this conference, presenting to such a passionate open source community. My name is Kuan-Yu Chen, and I am currently a senior design engineer in the RISC-V team at TensorRent. Good afternoon. It is a pleasure to be here at this conference, presenting to such a passionate open source community. My name is Kuan-Yu Chen, and I am currently a senior design engineer in the RISC-V team at TensorRent. Today, I will be introducing the Ocelot project, an open source project that enables RISC-V vector extension support to the BOOM core. The story behind Ocelot is deeply intertwined with my own journey. I worked on the second generation of the project during my internship. After completing my internship, I rejoined TensorRent full-time, and I've been one of the main maintainers of the project, working alongside a team of incredible engineers. In this talk, I will not only dive into the technical challenges and solutions involved in enabling vector extensions on the BOOM core, but also share the insights I've gained about open source hardware development. By the end of this session, I hope to inspire more people from the open source hardware community to explore projects like Ocelot and push the boundaries of what open source collaboration can achieve. Let's get started. Before we dive into the Ocelot project, let's first answer a simple but important question. What is the BOOM core? BOOM stands for Berkeley Out-of-Order Machine. It is an open source RISC-V processor core developed at UC Berkeley. The BOOM core is an out-of-order superscalar CPU, which makes it powerful and suitable for our project. What sets BOOM apart is its customizability. You can configure architectural parameters like the instruction issue width and memory interface width, making it suitable for a wide range of workloads, from research platforms to FPGA prototypes and even full ASIC tapeouts. On the right, you will see a block diagram of the BOOM architecture. If you have experience with modern out-of-order processors, many of these components will look familiar. There is the front end with the fetch and decode units, a reorder buffer, issue queues, and of course, execution units for integer and floating point operations. The BOOM core is integrated into ChipYard, an open source SoC development framework also developed at Berkeley. ChipYard provides a cohesive environment for design simulation, testing, and integration with other IP blocks. It is what makes experimenting with designs like Ocelot so much more accessible to researchers and engineers. I have included a link to the official BOOM documentation here on the slide. The maintainers have done a great job providing clear and thorough technical guides, which are invaluable during our work. Our project, Ocelot, builds on top of this ecosystem. Specifically, we aim to extend BOOM to support the RISC-V vector extension, or RVV, bringing powerful SIMD-style parallelism to an out-of-order architecture. Now, let's talk about the why. Why do we need to support the RISC-V vector extension in the first place? The BOOM core, as we saw earlier, is already a capable scalar processor. It handles general-purpose computing tasks efficiently. But in today's workloads, scalar execution often isn't enough. This is where vector processing comes in. The RISC-V vector extension, or RVV, allows a single instruction to operate on multiple data elements in parallel. This is fundamentally different from scalar processing, where each instruction works on just one data element at a time. You can see a simplified example of this on the right side of the slide. Instead of writing a for loop that iterates through each array element one by one, say to compute C equals A plus B, a single vector add instruction can perform the same operation across an entire chunk of the array in parallel. That is a massive boost in throughput, especially when scaled to larger datasets. This is crucial for modern workloads such as AI, machine learning, scientific simulations, and multimedia applications, where data parallelism is key to high performance. By integrating vector support into Boom, we are enabling it to tackle these data parallel workloads heads-on. We are essentially transforming Boom from a general-purpose CPU into a much more versatile compute engine, capable of handling modern compute-intensive tasks with efficiency. And more importantly, we are doing this in a way that is open source and accessible. This makes it possible for researchers, educators, and hardware developers around the world to experiment with real-world vector workloads on a customizable out-of-order core. Most of the open source RISC-V CPUs that support the vector extension today are in-order cores. These designs are typically simpler and easier to implement, which makes them a natural first step for exploring RVV. However, they also come with important limitations, particularly when you are dealing with complex workloads that have branching logic, memory latency, or variable length operations. On the right, we have shown a conceptual comparison between in-order and out-of-order processing. In an in-order core, instructions are fetched, decoded, and executed strictly in the order they appear. If one instruction stalls, say waiting for memory access, all following instructions are blocked, even if they are independent. Out-of-order execution, on the other hand, is smarter. It dynamically schedules instructions, reorders them, and tries to keep execution units busy as long as the dependencies allow. This becomes especially valuable when working with vector code. The Boom core is also superscalar. It can issue multiple instructions per cycle and reschedule around stalls dynamically. This means better pipeline utilization, higher instructions throughput, and ultimately better performance, especially on real-world applications with irregularities. However, combining these powerful features with full vector support introduces significant technical complexity. From handling long latency operations to managing hazard detection and scoreboarding, there are many challenges under the hood. And that's exactly what makes the Ocelot project both ambitious and impactful. We are tackling one of the harder problems in open source hardware and making it available for the broader community. The Ocelot project has evolved significantly over time. What began as a tightly coupled prototype has grown into a much more modular and standards-aligned vector processing system. The first version, Ocelot 1, was the initial proof of concept. The goal was simple: get vector support working on Boom. To do that, the team developed a custom vector processing unit, or VPU, and directly connected it to the Boom core. This tightly coupled integration allowed the scalar core to issue vector instructions and offload them to the VPU for execution. While it worked, this design was very specific and rigid. It tightly bound the Boom core to a specific VPU implementation. That meant it was hard to reuse or replace components. So, for the next iteration, we decided to rethink the architecture. That brings us to Ocelot 2, which is the generation I worked on during my internship. In Ocelot 2, we adopted the Open Vector Interface, OVI, as the communication layer between the scalar core and the VPU. The OVI is an open source interface standard originally developed by Semidynamics that defines a clean, decoupled protocol for how a processor core and a vector unit can talk to each other. This shift to OVI was a major architectural improvement. With OVI in place, both the Boom core and the VPU became modular components. That means you can mix and match, plug in different VPUs or scalar core, as long as they speak OVI. This opens up a lot of flexibility for research and development. You can, for example, compare different VPU designs or upgrade the scalar core without needing to rewrite the entire system. From a community perspective, it also promotes collaboration. Teams across different organizations can now build to the same interface and share components more easily. Beyond just adopting OVI, we've also introduced targeted optimizations, especially for vector memory instructions, and continue to improve Ocelot for more robust and efficient vector processing. Here we have the high-level architecture of Ocelot 2. On the left side, we have the Boom Scalar Core. This is the out-of-order superscalar CPU that handles all general-purpose scalar instructions, branches, integer math, control flow, and so on. On the right, we have the Vector Processing Unit, VPU. This is a dedicated unit that executes vector instructions. These two are connected through the Open Vector Interface, OVI. When the scalar core decodes a vector instruction, it passes it over to the VPU via OVI. The VPU handles the actual execution, and once the operation is done, the VPU updates the scalar core's reorder buffer, which ensures that instructions retire in program order and that exception handling remains consistent. This decoupled setup brings several advantages. For one, it separates concerns. The scalar core doesn't need to micromanage vector execution, and the VPU can evolve independently. It also simplifies debugging and testing, since you can simulate or even replace one side of the interface independently of the other. One thing to note is that you can see at the bottom left of the diagram, the scalar and vector operations share the same load store unit, or LSU. We added a vector load store unit, VOSU, that acts as a bridge between the VPU and the LSU. It translates vector memory requests into a format that the shared LSU can service. The VOSU handles address generation for various access patterns, and the LSU ensures that memory access from vector instructions respect the same ordering and protection rules as the scalar side. Next, we will look more closely at the VOSU itself and the specific challenges we had to solve to make it performant and correct. One of the biggest challenges in any vector processor is memory access. Even if you have a wide high-performance vector execution unit, its throughput is often limited by how quickly you can feed it data. This is especially true for data parallel workloads, where large arrays of matrices need to be moved in and out of the processor constantly. In Ocelot 2, we focus heavily on optimizing vector load store handling. The vector load store unit, VOSU, is shown in the diagram on the right. The VPU issues a vector memory request and it's broken down by the VOSU into scalar-like accesses, allowing them to integrate seamlessly with scalar requests through the original load store unit of the Boom core. From the LSU's perspective, it is just seeing a stream of smaller memory requests, which means we can reuse the Boom's mature out-of-order memory system. Inside the Boom LSU, we added dedicated load and store queues for vector operations, while leaving the existing scalar queues intact. This separation prevents vector traffic from stalling scalar memory operations unnecessarily. At the same time, it minimizes how much we had to modify the proven LSU design, keeping the scalar core's behavior stable and reliable. To further improve performance, we also introduce vector-specific optimizations. The first one is request packing. For smaller data types like 8-bit or 16-bit elements, the VOSU packs multiple elements into a single memory transaction. This ensures we fully utilize available bandwidth instead of issuing a flood of tiny, inefficient requests. The second one is mask skipping. Vector instructions often have mask bits, which specify which elements are active. The VOSU can skip masked off elements in bulk, reducing wasted cycles and memory traffic. Together, these optimizations reduce memory stalls and keep the VPU fed with data, which directly translates into higher vector throughput. These enhancements together greatly reduce memory bottlenecks and led directly to significant performance improvements. To wrap up the technical deep dive, let's take a look at some performance results. On the right, we have a table comparing the performance of Ocelot 2 versus Ocelot 1, across a few representative vector benchmarks, including convolution, inner product, and matrix multiplication. On average, Ocelot 2 achieves a 300% speedup over the earlier version. So where do these gains come from? First, from the optimized vector low-store path, which we just discussed. By efficiently translating vector memory operations and packing them where possible, we reduced memory stalls and kept the execution unit busy. Second, from the clean modular interface via OVI. This allowed the VPU to operate more independently, without needing tight coupling or ad hoc communication with the scalar core. It also simplified the control logic and improved scheduling flexibility. And finally, by keeping the boom core's low-store unit largely intact, we benefited from a well-tested, high-performance memory backend, avoiding regressions or unnecessary redesigns. That wrapped up the technical details and results of the Ocelot 2 project. I collaborated with another intern on this project during a 3-month internship. Looking back, I truly believe that this project is an ideal fit for interns or newcomers to hardware design, and here's why. First, it is a standalone project. The vector processing unit and the OVI interface form a self-contained design space. This means you don't have to touch every part of the system to make meaningful progress. You can focus on a well-defined component, which is really valuable when you only have a few months. At the same time, Ocelot is built on top of Chipyard, the open-source SoC development framework from Berkeley. Chipyard brings with it a mature simulation and verification environment, including test harnesses, runtime tooling, and debug infrastructure. That means you don't have to spend half of your time building scaffolding just to get your design running. You can plug in your module and immediately start testing. This combination of independent ownership and strong infrastructure support is rare, and it's exactly what made it possible for us, as interns, to ramp up quickly, contribute meaningfully, and see the results of our work in action. Tenstoran is committed to supporting and contributing to the open source community. For example, our AI compilers are fully open source, and the Ocelot project is one of our open source hardware initiatives. Throughout my work on Ocelot, I've also been reminded of how much we ourselves benefit from the open source ecosystem. In particular, we have relied heavily on frameworks like Chipyard, which provides a scalable infrastructure for simulation, testing, and integration. We also utilize Whisper, which is Tenstoran's own open source instruction set simulator for RISC-V. These resources and tools not only accelerated our development, but also connected us to a wider community of contributors. Next, I would like to share some insights from these open source experiences. One of the most important factors that enable the success of the Ocelot project is the use of open standards. Both RISC-V and the OVI are open specifications, freely available, fully documented, and developed in the open. Anyone can read them, implement them, give feedback, or contribute improvements, and that openness fundamentally changes how we build. With open standards, we could engage directly with the communities and developers behind them. For example, during Ocelot 2's development, we encountered a few ambiguities in the OVI protocol. Instead of being blocked or guessing, we reached out directly to the OVI maintainers on GitHub. Open standards also promote collaboration and longevity. Because OVI is an open protocol, any team building a vector unit or scalar core can adopt it, and know they'll be compatible with others. This makes the ecosystem stronger as a whole. Another major strength of open source development is the ecosystem it creates. In the case of Ocelot, we didn't start from a blank slate. Instead, we built on top of two powerful open source foundations, Chipyard and Boom. Because both of these projects are fully open source, we had direct access to everything, from the actual RTO source code to detailed documentation, simulation frameworks, test benches, and even historical discussions and commits that show how the designs evolved. Instead of guessing at architectural intent or spending months re-implementing basic infrastructure, we could study real design decisions, see how others had approached similar problems, and learn directly from their solutions and their mistakes. Open source ecosystems also encourage collaboration and reuse. As we worked on Ocelot, we were able to integrate with tools, modules, and utilities built by others in the RISC-V community, and in return, we contributed improvements back into the ecosystem. Instead of spending all our time reinventing the wheel, we can focus on improving Ocelot. Beyond the hardware itself, one of the often overlooked strengths of open source development is the availability of powerful, accessible tooling. The Ocelot project made full use of this, thanks in large part to the fact that Chipyard is designed to work seamlessly with a fully open source toolchain. One of the most central tools in our workflow is Whisper, an open source RISC-V instruction set simulator developed by Tenstorrent. Whisper lets us simulate programs quickly at the instruction level, which is incredibly helpful for debugging, validating instruction behavior, and checking edge cases before we even get to the RTO level. For RTO simulation and viewing waveforms, Varilator and GTK Wave are open source tools that are available. Together, these tools form the complete end-to-end open source toolchain, from high-level validation to low-level debugging. That makes our work transparent, reproducible, and shareable, all of which are core values in both engineering and open source culture. While open source development brings enormous benefits including transparency, collaboration, and flexibility, it can also come with some very real practical challenges. One of the biggest hurdles we faced early on was simply getting the environment set up. As many of you may know, setting up Chipyard along with all its toolchains, simulators, and dependencies can be a complex and time-consuming process. It often requires a specific set of tools, versions, environment variables, and build steps. For someone new to hardware development or even just new to the project, this initial ramp-up can be daunting. During my internship, we ran into this firsthand. Every new contributor had to spend significant time configuring their machine before they could even begin meaningful development. To address this, we created a pre-built container image that packaged everything needed to work on Ocelot. By standardizing the setup in a single image, we were able to skip the installation pane and focus immediately on building, testing, and iterating. It also meant we could share a consistent environment across different machines and teams, reducing the "it works on my machine" problems. Most importantly, this container image is now publicly available, so that anyone who wants to explore or contribute to Ocelot can do so with just a few commands. No complex setup required. This approach lowers the barrier to entry, especially for students, interns, and new contributors. One of the more emerging benefits of open source development, and something I found particularly helpful during my internship, is how it enables the use of AI-driven tools in a safe and productive way. For example, Ocelot and Chipyard are written in Chisel, a powerful hardware description language based on Scala. Chisel offers a lot of expressive power and parameterization, but for someone new to it, like I was, it comes with a steep learning curve. Traditionally, learning a new hardware language meant reading documentation line by line or relying heavily on mentorship. But thanks to recent advances in AI coding assistance, I was able to accelerate the learning process significantly. These tools became a kind of on-demand tutor, helping me explore and navigate a large code base without having to constantly pause and ask for help. And more importantly, since the code was public, there were no confidentiality issues. To wrap things up, I want to take a moment to reflect on the journey of the Ocelot project and what it taught me about open source hardware development. From the very beginning, openness has been at the heart of this work. We built Ocelot on top of open standards like RISC-V and the Open Vector interface, allowing us to collaborate and build confidently. We relied on a rich ecosystem of open source tools and designs, from Chipyard to Boom to Whisper, which accelerated our development and helped us avoid unnecessary reinvention. and we embraced modern workloads, including AI coding assistants, which helped us learn faster and work more effectively, without the risks or barriers of closed development. I would encourage anyone interested in computer architecture or hardware design to get involved in open source projects like Ocelot. It is a great way to learn, contribute, and connect with others driving innovation forward. If you have any questions about Ocelot, you can always reach me at the email address listed here. Thank you for listening and have a nice rest of your day. Thank you.